Hello to all of you and welcome back to my SP2 channel. This is going to be my last video for this chapter. Okay, there's going to be an introduction. We need to talk about the interaction between the 2s and 2p orbitals and how this is affecting our molecular orbitals. There's going to be a short lesson on the electron configuration and the molecular properties, and I will nicely summarize everything for you at the end. Starting with our introduction. So as you probably remember, the energy orbitals for the 2s and 2p are different, right? The 2s orbitals are much lower in the energy than the 2p orbitals. And as a result of that, when they are forming the MOs, the molecular orbitals, right? The ones from the 2s end up below the ones from the 2p, okay? Now, if you think about your 2p orbitals, they have different orientations, right? So consider the 2pz. That is the one that is always pointing along the bond axis, and it's going to have a very good overlap, right? Strongly bound than the 2px and the 2py orbitals, because those are the ones that are pointing sideways. This makes the bonding of the sigma 2p orbital lower in the energy than the pi 2p orbitals, and similarly, the anti-bonding or the sigma star 2p orbitals ends up higher in the energy than the anti-bonding of the, pi star 2p orbitals. Okay, so this is something that we have to consider when we are drawing our molecular orbital diagrams. Okay, now the last one that I want to kind of remind you here is about the degeneracy of our orbitals. Degenerate means that they have exactly the same energy level. So when you're looking at your pi 2p orbitals, right, there are two of them that they both are going to be with the same energy, right? We call them doubly degenerate, and that will be the same for your pi star, right, 2p orbitals. These are the ones that they're going to have two copies of the same orbital with exact same energy, okay? Cool. Okay, so far we have been drawing the MO diagrams, assuming that the 2p orbitals and the 2s orbitals do not mix. In reality, yes, there is an interaction, so we have to consider that. When a 2s orbital of one atom is interacting with the 2p orbitals of another one, they're going to be slightly shifting in the energy. Okay, so here is a thing that I want you to keep that in mind. The sigma 2s orbital goes down in energy, right? More stable. The sigma 2p goes up in energy, less stable. This effect is known as sp mixing or the 2s2p interaction. Now, how this is affecting the molecular orbital, it's depending on the size of the atoms. For boron, carbon, and nitrogen, the sigma 2p is above the pi 2p orbitals, right? So that means we do have this mixing. But for the oxygen, fluorine, and neon, the sigma 2p is below the pi 2p orbital. So there's no mixing here. So in summary, the sp mixing matters for the lighter atoms, boron, carbon, nitrogen, right? But if you look at the heavier ones, such as oxygen, fluorine, or neon, they're going to be normal, right? And we can always figure out the bond order by filling the MOs step by step, okay? Cool. So here is an example for the MO orbitals, right, the diagram. And I'm going to show you that for oxygen, okay, so for O2. So there are going to be two electrons in my 2s atomic orbitals, and they're going to interact, and they're going to form these two bonding and anti-bonding molecular orbitals. Now, for the p orbitals in my oxygen, I'm going to have 1, 2, 3, and 4 for each of them, right? And they're going to be 8 electrons here. So 2 of them goes in the sigma 2p, and then 1, 2, 3, and 4. These are my degenerate orbitals for the pi 2p. So that's 6. I still have 2 of them, and they should go in my pi star 2p. Okay. Okay, now let's talk about the electron configurations and how we can use that for understanding some of these molecular properties. I'm going to start by the magnetic behavior. How a substance responds to a magnetic field can give us some understanding about the electron configurations. If I have paramagnetism, that means molecules with unpaired electrons are attracted to the magnetic field. The more unpaired electrons, the stronger the interaction is going to be. Diamagnetism is pretty much the opposite. Molecules with all paired electrons are weakly repelled by a magnetic field. Okay, now if you're looking at your period 2 diatomic molecules, their magnetic behavior match with their electron configuration that you get it from your molecular orbitals. In short, paramagnetism indicates unpaired electrons and diamagnetism indicate all paired electrons. So take a look at your B2 boron where we have 6 valence electrons here. Your electron configuration is going to be the following. As you can see, you've got sigma 2s, and then there are 2 electrons here, and then we have sigma star 2s with 2 electrons. And then for your pi 2p x and y that are degenerate, each of them is going to have 1 electron. When you calculate the bond order, it would be 1, which means that we have a weak bond, right? And because we have unpaired electrons, they're going to be paramagnetic. If you look at C2 carbon, right, you're going to add more electrons here to continue adding electrons to your, pi 2px and pi 2py, right? The bond order would be 2 here, and it's going to be a double bond. And because we don't have any unpaired electrons, it's going to be completely diamagnetic. You can continue doing that for like N2, right, where we have 10 electrons. That is going to give us a 3 for the bond order. That's a triple bond, which is quite stable. And I'm just going to give you the energy here, the bond energy as your reference, presenting the strength of this bond, right? We can continue for like oxygen where we have 12 electrons, right? And that is going to give us a double bond. There are 2 unpaired electrons, so that's why oxygen is paramagnetic. Okay, and then you can do that for like F2 or Ne2 the exact same way. Now, if you ended up getting 0 for the bond order, just like what I have here, that means this molecule does not exist. It's not a stabilized molecule. Okay, cool. So here is a really nice summary table for you for all the diatomic molecules on the second period of the table. I would recommend you to like draw the molecular orbitals for yourself, right? And then kind of check them with the table here. Make sure that you know how to calculate your bond order. Make sure that you know how you can make comments on whether we have diamagnetic or paramagnetic for these important diatomic molecules. Okay, so that is the end of our molecular orbital theory. Thank you very much for watching this video. This is our last lecture for this chapter. There are going to be more coming up on the next chapter soon. Stay tuned for that. Take care of yourself and bye-bye for now.